The problem is cutting those patterns. It's very, very difficult to do using ARF, and so that's what I talk about. So I just showed you a method by which you can, extend your ability to pattern using existing equipment, existing wavelength for the foreseeable future. So what's the problem, right? 1D structures scale, kinda. They don't scale from a lithographic standpoint, but you have all these other tricks that you can use to keep making smaller features. The problem is 2D structures don't scale very well at all, right? And so that again is related to your scanner is basically a low-pass filter. It doesn't do high frequencies very well. So any kind of sharp corners like that, any small two-dimensional features are not going to look anything like they're drawn. Right? So they're going to have all these curves. And these kinds of feature sizes, you want these things at close proximity to each other. They don't end up that way. They all end up pulling back. The rectangles turn into ovals. So for tight two-dimensional patterns, it's very, very difficult to print this with a single exposure. And all the tricks in the world won't help you there, right? Because there's really no way to make those kinds of structures using pitch division and stuff like that. So the only way to do this is to say, if I need to put these two rectangles very close together, or if I had 4 of them and I need them put close together, I'll take 2 of them and put them on one mask, the other 2 on the other mask, and then interleave them, sort of the other trick that I talked about. That's really the only way to achieve any semblance of fidelity. It's impossible to print these things with a single exposure. So, this whole approach of extending ARF lithography breaks down when you talk about 2D features. At least with a single mask. You have to do all kinds of complicated stuff. And so the outcome is you have an explosion of masks required to deliver your scaling, right? So, you can't do it with one mask. You may need 3, 4 masks, right? So now if you have a layout, instead of using one mask to expose that layout, you need 5 masks. And you just can't afford it. So this is what I'm talking about, right? So you have one mask to print your grading, right? Using any of those techniques I showed earlier. Now you got to figure out how to cut these things, right? And so all these things are way too close together, right? All the cuts are sitting next to each other, and I can't print, 2 of those cuts. They're too close together, so I'll have to put them on different masks. So here I've shown the number 1 is your grading mask. So I have one mask to print the grading. I come back with a second mask to print 2 of those cuts that are shown in number 2. 2 and 3 are too close together. So these two cuts are too close together. So I'll have to put them on different masks. So I need a mask number 3, and then I got mask. If you look at that 4 cuts that are like a diamond, I can't put those on one mask. So I'll have to put them on essentially 3 or 4 different masks, depending on how close those cuts are. Right? So now I got a problem where in order to create this layout, I need 5 masks on ARF. And this is hugely expensive. Lithography is the most expensive step, and I can't afford to print. If I have 6 metal layers, a gate layer, and a diffusion layer, and each of them requires 4 or 5 masks to print. Now I've got 30 masks just to print a half a dozen layers. It's impossible to afford. So the huge problem is, how do you deal with the cost and complexity? This is one way to do it, right? And so we're looking at this approach. And so it may turn out that this is the only way to do it because there are no alternatives. So we're spending a lot of effort trying to understand how to do this. But at the same time, as you can, it's really obvious, you look at it, there's got to be a better way to do this than just throwing masks at the problem. And this is, it's practical. It's technically feasible. It may not be what you want to do from a cost standpoint. So here's a perfect example. You want vias, contact holes at this tight pitch. You just split them into 2 masks. Print the first mask, etch it, come back and print the second mask. So you do your orange mask and then come back and do the yellow mask. And you can print holes. Not the greatest looking holes. There's pretty early effort here. But you can see that you have one population that's these things, and then you have another population which is the other one. And then if you interleave them just right, you can get tight pitch vias. So it's technically possible. Yeah.
Is alignment not a problem?
It's a huge problem. I'll talk about that in a second. Yes. So the question is, can this approach be extended? You have 2 passes, can you turn it into 3 passes, can you turn it into 4 passes? And yes, technically yes, we can demonstrate it in a R&D mode. The question is it practical to do at high volume? Is it affordable to do at high volume? So yeah, you hit upon the right point. Yes, it is feasible in principle, but what's the problem, right? So here I've shown, this could be a real layout. I've got metal lines going this way. I've got these vias that connect, the underlying, say, assume this is metal 1, the yellow ones. And then I've got a via landing on it, and then I've got a metal 2 coming on top, right? So what you can see is, all of these things have to make electrical contact to each other, right? So current comes along this yellow line, it goes up the via, and then comes down the metal line here, right? So if this via moves relative to that metal line, the overlap of the metal line and the via is going to be not as good, right? And so if it gets bad enough, then you're not going to have good electrical contact, or the resistance of the via is going to be too high or something. You're going to have a problem. And these things you can calculate. You can calculate saying if the error in this edge is this much, and the error in my ability to place the via perfectly is that much, then in worst case situation, I'll have this fraction of the via still in contact with the metal. So these are pretty trivial calculations one can do. The problem is that in the old days, you had this via that would align to this metal, and then this metal would align to that via, and then there's another via that lands on top of this that will align to this, and so on. So you had this sort of very linear case where mask B aligns to mask A, mask C aligns to mask B, and so on. Now you got this is where we are today, where you have some situations where you split a layer into 2 masks. So for example, I have 2 sets of vias, right? Via 1 and via 2, or rather, this via is split into 2 masks. So I have B1 and B2. So now I got 2 masks that I'll need to align to the lower layer, and then when mask C comes along, it's got to align to 2 different masks at the same time, right? So now my error has to be spread over, there's more variability, right? I've got 2 things underneath me that are moving in different directions, and I got to make sure I don't fall off either one of them. So it's a lot harder to balance those 2. This is where we are, this is where we're heading, right there. You've got your metal layer may be done in multiple masks, right? The grading is done with 1 mask, but these cuts here, this cut could be done with mask 1, that cut would be done in mask 2, and there could be more, mask 3, mask 4. So now my metal's got 3, 2, 3, 4 masks. Now I come up with my vias, and maybe I have 3 sets of via masks. Now I've got 3 via masks that need to align to 4 metal masks underneath, right? And then if you calculate the errors, it's just ridiculous. It's impossible to manage. So we're doing things like, maybe this via can only align to this one metal. So all the vias that go on one mask have to align to just the cuts on this mask and things like that. You can play all kinds of tricks, but it's very, very difficult to manage the reg. So overlay is probably the biggest reason why this kind of technique will have its limitations. So this is a non-trivial problem to manage when you go through the numbers. What will happen is you can design your layouts, but when you run it in high volume, you're going to have fails. You're going to have either electrical fails or you're going to have reliability fails, because what you have is you have a contact that's so poor that you keep pumping current through that contact. Eventually it'll fail. Like in 6 months it'll fail or whatever, which is even worse. You don't want to sell a chip and have it fail in a customer's PC. Right? So these are real problems that you have to worry about. So this is where EUV comes in, right? EUV has the ability, because of your lambda, your wavelength is so much lower. It has much better resolution, especially for 2D stuff. So I can take these 4 masks and make them all on the same mask. So all those cuts go on the same mask, and I can do pretty good end-to-ends, all these kinds of features. I can do very, very small contacts at tight pitch. I can do them all in single exposure. So EUV offers a tremendous opportunity for process simplification for cut and contact hole patterning especially. Right? Now, it can also print lines and spaces tighter, but there the benefit is much lower, because I can do pitch division for very little extra cost and get away with it. So the drive to use EUV for printing gratings is not that great. To me, that's not very exciting. But if I can replace 3 or 4 ARF masks with 1 EUV masks, now I'm starting to get pretty interested about how this is going to work out. And so the promise of EUV, of course, like I mentioned, is very high K1. Your lambda is pretty much lower. So you can have a single exposure, OPC, a lot of the proximity corrections, things you have to do to manage the patterning is much simpler. So you can get much better design rules. You can allow the designers to do things that you forbade them to do on the previous, unidirectional layouts. Maybe you can go back and let them do bidirectional layouts, and the designers will love that. So there's a lot of flexibility that EUV brings to the table. Of course, EUV is a horrendously challenging technology. Pretty much every component in the chain of things that you need in lithography has to be touched. The source is very different. You need a huge laser that ignites a plasma to generate the light. Giant problem. You need the masks, because EUV goes through everything. It's almost like an X-ray. It's getting close to that wavelength. So you need reflective masks, very special kinds of masks. The standard masks don't work anymore, so you got to change the mask. The optics are completely different, the scanner optics, and the photoresists are different. They work very differently. So everything has to be changed in EUV, and every one of them is a non-trivial problem. But then again, we have a lot of data. This is EUV photoresist. You can print fairly tight pitches. These are 30, 35 nanometer pitch features. Good, very nice contact holes. So from a EUV resist resolution standpoint, I think we're on a good path. I think we can get fairly good performance from EUV. It's not enough. If you look 3-4 generations, it's probably not enough. But I think for the next 2 generations, I'd say we probably have photoresist performance that at least looks reasonable, looks promising. EUV masks, like I mentioned, are very different. They're reflective masks, not transmissive masks. So we have to figure out how to make these masks. And EUV mask defects are a huge problem. You can't have defects on the mask because they will print on the wafer, and then it's probably the worst kind of defect you can have, a defect on a mask, because it'll kill every die on the wafer, right? Because you're printing the same pattern over and over on the whole wafer. So it's very difficult to make clean EUV masks. So we're still struggling to reliably make masks that have 0 defects on them. So which is obviously not where we want to be. So we're very close, but we're not quite there. So a lot of work is needed to make clean masks, right? So there's a huge R&D effort trying to figure out how to make very good EUV masks. It's a key technical challenge. Line width roughness is a huge concern with EUV. So this is what ARF photoresists look like, very nice and smooth photoresist lines. This is what a EUV line width roughness looks like, comparable feature size, so much rougher. And so what does roughness do? Roughness, especially if you think about a gate layer, it changes the width of your transistor gate, right? It introduces variability. Right? And so that will directly result in variability in your transistor parameters, saturation current and things like that. Right? So highly undesirable. And so where does this LWR come from? A variety of things, right? You have noise, you have flare in the EUV optics, which are considerably worse. We have shot noise from EUV, from the source itself. You have blur from the photoresist, how the chemicals in the photoresist move around, and so on. So there are a lot of different reasons. So EUV resists, they've improved quite a bit, but they have a long way to go to catch up with the ARF photoresists. You can do all kinds of post-processing to clean this up, but it's never quite perfect, and obviously that's again another costly step. So we need a lot of fundamental work. This is a subject of fairly intense research, how to get line width roughness to be better than where we are today, more in line with ARF. You can, like I said, do things in the fab. This is what you start off with in lithography. Then you come up with different techniques using etches and film depositions and so on to make things a lot smoother than what you start with. But still, I'd say we're still not quite where ARF is, even with their best techniques. the biggest issue right now facing EUV is our inability to get enough light. Like I said, the EUV source is a very, very complicated thing. ARF is a laser, argon fluoride laser that generates enough light to eliminate your photoresist. EUV is a very different technology. EUV, the way EUV works is you have a huge laser, and then you have a tin droplet that you have to drop through this vacuum, and you hit that tin droplet with this big laser pulse, and basically you create this plasma. You ablate the tin and create this plasma, and that's what generates your UV light. Okay, so it's a, so these droplets are falling at a very high rate, thousands, kilohertz rate, and then your laser is firing at that same rate, and you got these control systems that steer every droplet in the right place so that it can be hit by this laser pulse to generate the light to eliminate the wafer. Right? So it's a very, very complex system, and generating enough light has proved to be a huge technical challenge. So for example, we say we need about 250 watts of power coming out of the source to get the scanner to run at the correct run rate. We need the scanner to run at, say, for example, 100 wafers an hour. If you say that is the economically reasonable standpoint. If I have a scanner in my fab, I need it to process 100 wafers an hour. So I need enough light to be able to process 100 wafers an hour. The problem is right now, sources are putting out 10 wafers, 10 watts, not 250 watts. So I need to get from 10 watts to 250 watts as soon as possible so that it becomes economically feasible for me to put a scanner into the fab. The roadmaps have slipped badly. There are all these expectations of where the power needs to be. So this is sort of what we thought we were going to do. We'll have this power and then we'll jump up. But in reality, you end up with something like this, where even today we're nowhere near the kinds of powers we need to be, and sort of this is where we think we're going to end up, right? So if I don't have 250 watts or some number in that neighborhood until 2013, 2014, so that defines how soon EUV is going to be economically feasible. So lack of power remains the main impediment to putting EUV into HVM. So a lot of progress being made, no question about it. It's a very difficult technical problem, right? But again, we have to have enough power so that EUV is cheaper than 4 ARF masks, right? So that's sort of the yardstick you're going up against. If it's cheaper for me to print 4 ARF masks than 1 EUV exposure, then that's what we'll do. Right? So cost is a very, very important factor. And so why is source power important? Hitting upon that same point. So there are a lot of analysis that's been done on how much power is needed and what EUV is going to cost as a result, and so on. And a lot of this is speculative too, because we don't quite understand how much an EUV scanner, how much is it going to cost in dollars or cents to operate a scanner day in and day out, right? So if you look at some kind of cost per wafer, and you compare different types of scanners. This is your ARF, single patterning, double patterning, and so on. You say, if I can run EUV at 100 wafers an hour, the cost of my UV exposure is going to be quite a lot better than double patterning. Great, right? That's what we want. We don't want to do double patterning. We want to do EUV. But the big catch is, in order to make this 100 wafer an hour happen, you need 250 watts of power. If I get 25 watts of power, then I'm going to get 10 wafers an hour. And now all of a sudden, my cost is going to shoot up way past the double patterning bar. The actual units are really hard because it's very proprietary, right? Most of these analysis, and so it's usually people show comparisons because a lot of this is their own internal calculations. So these cost of ownership assumptions, how much is it going to cost, depends on a lot of assumptions, of course. What is the source power? If you have 168 hours in the week, how many hours is the tool actually up and running as opposed to being broken down, right? So the reliability of the tool goes into the equation, and then how much a reticle costs and all that kind of stuff. So it's a complicated calculation with a bunch of assumptions, but the bottom line is that the source power is a big driver of that bar. So if you don't have the right kind of source power, then you're going to affect the cost of ownership of EUV.